and I'm sure that there are one or two questions. But before that, I will say a few things, because I didn't expect that Sunita will do such a fantastic marketing exercise for New Zealand and Open Parallel. Can you please go to the slide number 2?
Yeah.
And because I've been creating multi-core world as a way to, then is the next one, perhaps, sorry.
This one?
One more? It's one. So is any local person recognize anything on this slide? So you will need to take photos now, because this is, I mean, the reason why, you can see that on a poster out there. So that's a artist-generated image, but this is the square kilometer array image, and that's what Open Parallel and New Zealand was involved. That was the genesis of multi-core world, right? So thank you for that. Now, would you be so kind to go to the slide of alpaca?
Oh, yeah, sure.
So, because the whole point that I'm trying to convince, particularly the internationals, is that we have the same talent in order to participate into these mega projects, right? So, yeah, software stack, a lot of stuff. You know what it stands for?
Mm-hmm.
Some Intel guy, perhaps.
Mm-hmm.
So this is threading building blocks. So when Intel had that, so now it's part of one API.
That's not on.
So Open Parallel was created under a contract for Intel. Well, not, I mean, I always say that Intel was an angel investor, but I mean, I founded Open Parallel to do a large project for Intel because they were open sourcing the platform, the tool, and well, they needed some approach into community. So we did a web performance. We worked over 2 years on this. So thank you very much.
Thank you. Thank you for putting things into perspective.
So it's something that it can be done from this little country of ours. So first question for Larry.
So first of all, thank you very much for the talk. For me, this was a nice example of a workflow, an integrated HPC ML workflow without talking about surrogate models. You're doing something else in terms of data reduction with it. So it's a very nice example. This question is maybe a little bit deep in a specific topic. And so maybe we should take it offline. I'll let you decide. I was curious about the comment about going down to the libfabric level rather than using MPI, and it sounded like it was for bandwidth concerns, and that's a little bit of a difficult thing to do. It's right, it's not intended to be an end-user API. It's intended to be a communication library API. Is there anything you could say about that, or if you'd like to take it offline, that's fine as well.
We can take it offline as well, but I think that is, I think I might have not done the connection right, but yes, it's more of the communication layer. We did a bunch of experiments trying to influx data and use both libfabric as well as MPI to experiment which could help us move data from node to node better. And then I think there were a bunch of low-level implementations that some of us tried but didn't go too far. And then we stuck to MPI for the time. But then there is so much more to do with libfabric, but it was more towards communicating from node to node to node.
Let's talk about alternatives later.
Sounds perfect, yes. I need suggestions.
Any other question? Lorena.
Yes, you mentioned on one of the slides towards the end scheduling and Slurm. So if you could comment on what exactly you would need from the system scheduler to help for such a complex workflow.
Good question, which means I don't know the answer. I think, looking at all of this on the left-hand side, right? Right now, we are dealing with one simulation from one experiment. But imagine there were so many physics experimental systems, and imagine there is an environment that is able to take data from these different experimental sources, right? And then there is data explosion with varieties of data. And then you need this system, the scheduling system at multiple levels, First off, data needs to be cleaned up, it needs to be prepared, it needs to be processed, analyzed, what have you. But then you need that scheduling system that can do these in-transit learning. Some can deploy an ML model. But right now, it's just one simulation. Now, throw many more complexities of data on the system, right? What kind of scheduling then we will need?
Okay.
And we're now talking about CPUs, GPUs, and now sooner or later, there'll be a quantum angle now. Yeah. How do we deal with any of this? So it's a really broader question, and I don't think there is an answer today, but something to think about.
This is beautiful for the scheduling community. I have one more question, if I may. Yeah. You mentioned many times that you were happy with your computer science hat, and then the physicists were happy later or separately with their physics hat and interest. So how do you publish work that makes both happy? Because you have the work, like both you and the physicists are now happy. So where do you publish this work that both communities benefit and appreciate it?
You're talking about marriage.
Yeah.
Yes.
Yeah.
Very good point.
It's tough. It's a long relationship. Thank you for asking. These are conversations that we have spent hours. So the IPDPS later this year does not have the physics. It's a balance, right? There is no perfect venue, which we have struggled. PASP was one way to go. But then we had so much physics going on, and without explaining the physics, the computer science doesn't make sense, vice versa. So for the IPDPS submission, which got accepted, it's a best paper nomination as well, we only had one column explaining the physics, which doesn't do justice to the physics, but it's IPDPS. So we focused everything else on the INN and the machine learning and the in-transit. So I don't think there is a perfect venue. So we have been splitting our work because we got rejected twice because we tried to pack so much. Then we were like, the audience is not receiving this. So we had to split it up. But yeah, something to think about.
So what you say, and sorry for monopolizing again, because this is really close to my heart. I mean, we went through this over a decade with the SKA in New Zealand and the world. And then later you also mentioned Destination E, Destiny, which is a project from the European Union about the digital twin of the entire planet Earth, but it's already flowed because it's mostly for the Northern Hemisphere. So I've been talking to, with some of the leaders of here and there. It's a fantastic idea, combination. What's the biggest flaw? They don't have their own compute. They rely on Euro for HPC or whatever the name. The moment that I say, hey, I have the experience of SKA, they say, oh, those guys are right. Why? Because the symbiosis between the radio astronomers and the computer scientists. It's not that you own the machine, but you have a direct communication between the problem and the solvers of the problem, whilst you would just say that, okay, then Destination E, I don't know. I had this conversation 2 years ago, but I don't know if they are being happy. Yeah. And I'm talking about a 200 million euro project. Yeah. Sorry, Jim.
Yes, Sunita, you gave the answer which I would have recommended, which I think we see oftentimes in multidisciplinary teams, that you publish in the best physics conferences or journals for the aspects and the advances that are relevant for that community. And you publish in the computer science or the architecture journals and conferences for that community. And that happens often in these multidisciplinary teams. Yeah. So it's very good.
Yeah, and it takes years. This whole 4 or 5 years of work took time to write it up and set it out.
Before I give the word to Jeff, it's also to everyone involved. We have a new audio system, so I encourage everyone to speak as close as possible to the microphone.
Yes, I'll try that. I just had a question. I mean, it was impressive that, you took the load up on the system from 8 megawatts up to 23 megawatts. So it looks like you're using the entire machine at Oak Ridge. Yeah.
Yeah.
Can you just talk a little bit about how difficult it is to access and schedule that entire machine, and what can you do on the way? Can you do halfway up there to learn some things about scaling the work?
Yeah, for sure. I don't have those plots and results, but we did do that. Like it went back to the configurations, the parameters, the hyperparameters that we could set. The other interesting part we learned was what you think scaled up until, say, 400 nodes, it didn't keep up to 4,000 nodes. So we lost many things in the cracks, as you can imagine. But we didn't quite go in depth at every level. So there's a scalability plot, but they can imagine to do that what happened at 100, 400, 800, 1600, so on and so forth. But we did do some minor experiments and we couldn't scale. Like the entire configuration had to be redone if you threw 100 more nodes to it. And the power, it did jump from, it was varied, like 8 to 23, maybe there was a 10 in between, there was a 12 in between, and maybe it scaled down all of a sudden. So there were, ups and downs. So we thought, okay, that's a whole different story going on there. So we didn't go deeper, but that's on our to-do list.
Okay.
Thank you.
Please join me saying thank you to Sunita
Thank you.
for a wonderful presentation. So that we need to give this one.